And today, I was noticed a lot of your background was in like more empirical side. So I choose this topics which is more about a bit like light on the game theory. I don't know how many of you have like a game theory background, but this thing will be mostly like a pretty I would say not very difficult, not very hardcore. So if you have any questions and don't feel embarrassed, just raise your hand and let me know like your question. I'm happy to answer. Okay, so today my talk will be on beyond equilibrium learning. For those of you who have heard some of game theory, you probably know like game theory, most of game theory, or a lot of big chunk of game theory is about like learning Nash equilibrium or learning some stackrable equilibrium, correlate equilibrium, a lot of other equilibrium. So today we'll talk about why we want to go beyond the equilibrium learning and what is the algorithm to do it. Okay, so we will start with talking about what kind of problems this talk will concerns, or what kind of target applications we have in mind, although we're doing like more theoretical work. Because the game theory, so most of the applications will be on the multi-agent decision-making problems, like including the Go and StarCraft. You probably already heard a lot of great story from DeepMind. They already achieved like superhuman performance. But most of those games are two-player games. But there are also a lot of more complicated games, like in real life, like multiplayer games. For example, we want to play Texas poker. It's not just you against the other player, but you have a 6-player or 7-player on the board, and you're trying to like learn everyone. Like everyone is also adaptive. Like they will learn your behavior and they adapt their strategy. And similarly, there are like you can also imagine in the future you want to control a troop of drones, and the drones each will like coordinate with each other or collaborate with each other. So those systems are, in general, it's like we have more than one agent. It can be 2 agents, but it can also be multi-agents. And we want to have the ability of handle adaptable opponents. So in all those applications, and all the opponents are highly adaptive. So we cannot treat them as a stationary environment and just beat the stationary environment. No, we cannot do that. We need to adapt to their strategy change. Okay. So today, because we're focusing on game theory, so we need to talk about what is the mathematical models we're gonna use to learn the like study the games. So this talk will just focus on the very simple model, which is called normal form games. I think you will learn these models from the very entry course of game theory. So essentially, the normal form game is saying like we just represent the game in terms of matrix if it's 2-player game. But if it's a multiplayer games, you can think about a tensor. So let's just think about a 2-player game as an example. So if we have we're playing rock paper scissors among 2 players, essentially we can represent this entire game as a matrix where rows corresponding to the action of the first player, while the columns correspond to the action of the second player, and where each entry corresponds to the payoff or the reward of each player. Like the left entry is the payoff of the first player, and the right one is the payoff of the second player. So in this case, we know rock beats scissors. So this top right entry is like 1 minus 1. And similarly, paper will beat rock, so it's minus 1, 1. So you can look at this entire payoff matrix and know what is the rule of the game. This is for the 2-player game, so you can represent it as a matrix. But you imagine if you have 3-player, it will be like a 3-dimensional tensor. And if you have 4-player, it will be like higher order tensor. Okay. And in general, mathematically, you can just replace these games as a one utility function, where UI is a function of A1 to AN. Imagine you have N player. So you just put all the players' action, A1 to AN, as input of the function, and where this UI utility or UI function will return the utility for the ith player. Okay, so very simple model for the game, and no structure, like no transition or no nothing. So we just studied this very simple games. And the reason we talk about this normal form games is because, you know, like in practice, when we study Go or study StarCraft, those are sequential games. Those are not simple as states. They have states, they have transition. But if you don't care about the complexity, so you want to study this everything like solution concepts in a very high level, you can imagine like you can view all those policies in sequential games as an action in the normal form game. So policy means like when you see some status of your opponents and what is the reaction you're gonna do. So you just bundle all them together and treat it as one action in normal form games. In that case, you can even view sequential games as normal form games. So that means what I'm going to talk about today, all the solution concepts and how to be on equilibrium, going to also apply to sequential games. If you like ignore the efficiency issue, all the concepts we're going to apply there. Okay. Any questions so far? I guess.
So when you have sequential games, it means that you're going to have exponential number of possible actions.
You have exponential, yeah. So that's why I'm saying like ignoring the efficiency issue. Yeah. So today's overview will be very simple. So we first view what is a classical game theory or standard game theory, talking about like mostly about what is the standard equilibrium concepts and what are the learning algorithms to do that. And then we're going to talk about two I view very important scenarios where equilibrium concepts, classical equilibrium concepts are not enough, and why we need to what kind of additional criteria we need to care about, and what is the relation of this criterion to equilibrium, and what is the algorithm to achieve the new criterion. And two of them are like, one is the rationalizability. Essentially, we want to avoid dominated actions. And the other one is when we play a lot of symmetric games, we know for symmetry, those games are like every player is fair to every player. So every player is symmetric. And one basic objective is we want to just achieve the equal share. That is, if we're playing like 4-player Mahjong, and all we want is, for example, I'm gonna win 1/4 of the time. But we will talk about why standard equilibrium is not able to achieve that, and what is the additional thing we need to do to achieve that kind of goal. Okay, so first let's review the standard game theory. I just want to know how many of you have a game theory background, so I just want to decide how fast I'm gonna go over it. Okay, sounds good. I will just be moderate fast. So I think one very important thing about game theory, which makes it different from the standard learning theory, supervised learning, or some other stuff, is in the game theory, the optimal strategy becomes something very interesting. Because for standard reinforcement in single agent, for example, if the environment is stationary, so all you want to do is achieve the highest cumulative rewards. So this is like everyone agree on this objective. However, for the game, because your opponent is adaptive, so in terms of what is the optimal strategy, it becomes a bit tricky to answer. So there are a lot of solution concepts to it. And one very important reason is no longer just as simple as single agent setting, is because you just imagine in the rock, paper, scissors games. A lot of those games, strategy may no longer have this linear relation. That is, we no longer have one strategy that is the best. For example, in this rock, paper, scissors, you have a rock, beats paper, rock beats scissors, beats paper, and paper beats rock. So in this case, a lot of times you even have like some cyclic structures in it. So in that case, like defining what is the best strategy becomes a bit tricky. So there are a lot of discussion about it. And one of the commonly used notation is called Nash equilibrium. Okay, as you probably can read this from the Wikipedia, essentially we say a strategy, or usually we talk about a mixed strategy in a sense. The strategy means for the ice player means it's no longer we're just picking specific action, we're picking a probability over action, and we call this as a strategy, or we say it's a mixed strategy. So the definition of Nash equilibrium essentially is saying, first, the Nash equilibrium is everyone will play independently. So it's a so-called product policy. That is, everyone's policy is independent. And then the Nash equilibrium has a property that no player will gain anything by deviating from her own policy if other players are fixed. So if other players stick with the Nash policy, then you won't gain anything by deviating from your policy. So we can take a very simple example, look at the rock, paper, scissors, and we will easily see understand what is Nash equilibrium. In this case, it's 2-player, and the Nash equilibrium is just playing uniform probability over all 3 actions. That is, I will play rock with 1/3 probability, play scissors with 1/3 probability, and play paper with 1/3 probability. And you can see in this case, no matter if your opponent is sticking with this Nash policy or like this uniform policy, then no matter what you're doing, if you're deviating from your policy, you're still like having the average expected payoff 0, so you won't gain anything.
Okay, one question.
Yeah, please.
Hi. For this Nash equilibrium, do you need to know the other player's policy, or can is it possible to do it without knowing the other player's policy?
So we'll talk about the property of Nash equilibrium later in the two-player games. They do have some property which can ignoring what opponent. By its original definition, assuming all other players need to play the Nash equilibrium. And you can you reach equilibrium means like if your opponent play exactly this equilibrium and they stick with playing it and you don't gain anything by deviating it. So somehow it's kind of implicitly have some knowledge about other player need to play this strategy.
So you know the other player's policy in when they're playing it.
Thank you. Any other questions? Okay. So this is the standard thing equilibrium. I guess most of you even have no knowledge, like no background on game theory, probably have already heard of equilibrium. But some other concepts I will also want to introduce today, which is also related to this talk, is so-called correlated equilibrium. So I think the major difference of this correlated equilibrium versus like Nash equilibrium is Nash equilibrium, as I said, is a product policy. So assume each agents play independently. That is, although each agents pi 1, pi 2, pi m are mixed strategy, that is, each player is play some probability, but those probability need to be drawn independently. So their strategy are independent. Well, correlated policy actually allow them to play some correlated strategy. So they are no longer need to be independent. And the correlated strategy is especially helpful in the general sum game, which is no longer zero sum. So there are a lot of scenarios you will imagine some win-win is going to happen if you're playing correlated strategy. So we can just take a very easy example. Look at this modified rock, paper, scissors. So this black entry are the standard rock, paper, scissors entries, which essentially rock will be scissors, scissors beats paper, and paper beats rock. Well, I modify the entry where if P1 and P2 have the same action. In the original rock, paper, scissors, everyone at that time will draw, so both of them getting 0 reward. Here I modified both of them to get 1 reward. So you can imagine in this games, it is rewarding, or there's an incentive for both players to play the same action because they can actually get some social welfare from this game by playing the same action. So in that case, we can have a so-called correlated strategy. That is, both players have some coordination. They no longer play independent policy. They will play some random policy with this probability. That 1/3 probability, they will both of them play rock. 1/3 probability, both of them play paper, and 1/3 probability, both of them play scissors. So you can realize this probability can never be realized by some like independent policy. That is, if both of them have no coordination, have no no communication among each other, like you can never realize this because independent policy require like P1, the probability of this need to be factorized into like I think the product policy require this to be rank 1 matrix, but this is like clearly rank 3 matrix, so it's not a product policy. And whatever the correlated policy, as we see here, requires some coordination mechanism. So usually we realize there's a coordination mechanism by so-called shared random bits. So we just imagine there's a coordinator in the middle and they can toss some random coin in the beginning and or like roll some dice. For example, when you roll dice to be 1 point or 2 point, then every player play rock. When you roll to 3 and 4, every player play paper. So you have this kind of protocol in the front. This is like a shared randomness. Okay, any question about the concepts of a correlated strategy? So once you have correlated strategy, then we can talk about 2 more equilibrium, which is also very standard in the game theory. One is called a correlated equilibrium. So correlated equilibrium now is basically very similar to Nash equilibrium. The first difference is it no longer is a product policy. Now it's a correlated policy. So you don't need to be the product distribution. It can be some general probability over the joint action, where again, we have the same characteristic of equilibrium. That is, no player can gain anything by deviating from her own policy if other players just stick with this correlated equilibrium. And because we say when we realize this correlated policy, there's one additional thing is we need to have some coordinator in the beginning to roll some dice to show some shared randomness. So there's 2 variants of the equilibrium. That is, the first variant is if you betray others. So if you're already deviating from your own policy and you betray others, but you can still see the shared randomness, see the random dice from this coordinator. This is called a correlated equilibrium. And you can imagine there's another concept which basically when you betray, you can no longer see the shared randomness. And this is called a coarse correlated equilibrium. Okay. I won't go into the very subtle details on those why like the sharing randomness, able to see it or not see it, like makes a very big difference. But I think I just want to know there are two additional concepts, and there are some very simple relation between all those two. That is, yes.
Sorry, I have a question. Like when you mentioned the correlated policies, and it has for each policy, you have a probability, right?
Right.
So what do you think about if what is the differences if it's conditional probability, like if one player
Right.
have some policy to make some action, but the other players maybe.
Yeah, I think your question is very good. So basically, product policy would have this property that is conditional on one player's action. The other player's distribution would be the same no matter what the first player's action. And well, the correlated policy basically you can see here, conditional on one of the player's action, the other player's probability would actually change. So this is one characteristic of the correlated policy. That is, you can see the probability distribution are correlated. It depends on the other player's action. Well, the product policy is independent. Okay, yeah, this is a very good question.
So basically, your two equilibrium here is about whether you allow the change of, let's say, one policy condition on the others, or whether you allow the changes of the other policies when you make them independent to the others.
Right. Okay. Yeah, a good point. Okay. So very simple thing is I think okay, so we can verify. I think okay, I won't verify here, but basically we can see this policy is actually a coarse correlated equilibrium. That is, for example, if you betray and if you can no longer see the shared random bits, then what you can see is your opponent is actually playing uniform action. So in that case, this is like equilibrium. But on the other hand, it's not a correlated policy because if you betray and you can see the shared randomness, then you'll know exactly what is the action of your opponent is playing. So you can just play in the best response. For example, if you know the opponent is playing rock, you can just play paper and then you can beat them. So in that case, this is not correlated equilibrium. And in general, we have this relation that the Nash is smallest set. So whenever you have a Nash, it's always guaranteed to be a CE, but not vice versa. And what we also have is whenever you have a CE, that is also guaranteed to be CCE. So CCE is the largest set, while CE is smaller and Nash is the smallest set. And the reason we're gonna use CE and CCE a lot is because beyond two-player zero-sum games, Nash is actually proved to be computationally hard. Yes.
Sorry. Or you mentioned the correct equilibrium. So which means like you use the cases like if someone take the rock and another guy maybe know that the probability, so he will change to the paper.
Yeah.
So it's no equilibrium. So which means like it is for the three for these two players, it is no maximize its profit.
Right.
So you mentioned it is not an equilibrium.
It's not an equilibrium. Yeah.
Okay. Yeah. So it's for the whole group people.
Yeah, it's maximizing the social welfare, but it's not an equilibrium. Yeah. Okay. Yeah, as we mentioned, the Nash equilibrium, whenever you are beyond two-player zero-sum, which is like a very small class of games, it's proved to be so-called PPAD hard. That is, you cannot learn in polynomial time. So that's why in a lot of general games, you want to some concepts that is slightly relaxed Nash equilibrium. That is, you want to find a CE and CCE. All of them can be solved by linear programming. So those are very efficiently. You can efficiently find those concepts.
Okay.
Oh. Hello.
Okay, I guess there are some mic issues. Maybe Sharinja, you type your question online. I can ask for you. Yeah. Maybe you can turn it on and then I can read it. Okay.
So we just briefly go over all the equilibrium concepts, and then next we're gonna talk about how we're gonna find the equilibrium. So there are a lot of algorithms which were designed to find equilibrium, but for simplicity, I will just restrict for one of the most well-known class of algorithm, which is called a no-regret learning algorithm. So no-regret learning algorithm was originally not designed for games, but it was designed for another problems. But it turns out this is provide a very powerful tool eventually to the game theory, to learn the games. Okay. So this no-regret learning was originally designed for adversarial bandits. Okay. So what does adversarial bandits mean is you can just imagine you walk into a casino and you see like a bunch of bandit machine. So what your task is essentially you want to like pull each arms and we will measure like the success of how you pull it in terms of this regret. Okay. What does it mean is that at every round, basically you can imagine every T is like at a T's time, you're gonna decide a mixed strategy. That is, what is the probability you're gonna pull each arm? And then the environment, just imagine there's a very bad boss of the casino, and in the very back, he can actually tune this like probability of each machine to give you the reward. So they're gonna choose some adversarially loss. So this loss will be chosen before he see your action at T's time. But he can depends on your previous behavior. For example, if you always play the first arm, and he can make the first machine to have a huge loss or something like that. And so this is why this is called adversarial loss. And then regret is eventually measured against the best action in hindsight. So what does it mean is, so imagine in the history I recorded, I have like L1, L2, that is the adversarial loss for the first round, second round until the T's round. So eventually after I know all the loss, I can in hindsight determine what is the best action for all those loss. So my regret is gonna measure against that. That is, okay, if I know beforehand what are all the losses, what is the best action I'm gonna take, but now I don't know that, so I'm just doing some like random strategy or doing some smart strategy before that, and so I hope this regret would be small. So we can think this regret if I don't do anything, if I just do some terrible strategy. So basically, this will be something. This can be, in the worst case, will grow as linear with respect to T if loss is bounded. Because if loss is bounded, then this is bounded by 1 at each time, and the summation is bounded by T. So if you achieve some order T regret, this is like a trivial algorithm. So you're not doing anything. So we talk about a so-called no regret learning algorithm. That is, we say this regret needs to be little o of T. That is, asymptotically, when T is large, it needs to be scaled sublinear in terms of T. So in that sense, the average regret will go to 0. So it requires like no regret algorithm. So there are a lot of very simple algorithms can actually achieve this no regret guarantee. For example, one very simple algorithm is so-called a hedge algorithm. Hedge algorithm essentially just doing this so-called exponential weights update. That is, at every time T, you will have a probability over all the actions. So you denoted that probability by mu T A. That is, at T's round, what is the probability you're gonna play action A? So the updates is literally just at every step, you reweight this probability by the exponential of minus some learning rate times the loss of this action. That is, if you see this arm has a lot of loss, and you just penalize it by doing this exponential reweighting. And if some arm has very little loss, you will like increase the weights. If some arm has a very high loss, you will decrease the rate. And all you're doing is by this exponential reweighting. And you can prove by choosing some proper learning rates, you're actually able to achieve square root T regret. Okay, so it's no longer just odd, it's no longer just little o, it's actually square root of T. And the conversion of the no regret to equilibrium is actually turned out to be extremely simple. That is, we have a very strong guarantee if all players just run no regret algorithm independently. So we don't even need to say like all players need to play the same no regret algorithm, like play hash. There are like a bunch of different no regret algorithms. You can be no regret algorithm A, no regret algorithm B, no regret algorithm C. So if all the players just play some no regret algorithm, they can just play different algorithm. But eventually you can prove this average policy. That is, if you can like a product at the first round, all the players policy together, and then you're doing some average over all the different rounds. So this policy will eventually converge to a coarse correlated equilibrium for general sum games, for like multiplayer general sum games in the most general form. And more specialized cases, if it's two-player zero-sum games, you can further marginalize the CCE because CCE is this product policy. So if you just marginalize the probability to make it independent of each player, you can actually prove this is further a Nash equilibrium. And we already said, in general, finding Nash equilibrium is not possible. It's PPAD hard. So for Nash, it's like restriction two player zero sum case. So basically, if you don't really know this, yeah.
How much can you say about, like, depending on which specific no regret algorithm they use, which exact cross-correlated equilibrium they converge to, and if different no regret algorithms converge to the same cross-correlated equilibrium or like different ones?
I think this is a very good question. And so the answer is also a little bit tricky because which cross-correlated equilibrium actually depends on the problem structure a lot. So I think there's no general easy answer, but for some specific class of games or specific algorithm, probably you can say something by doing more like detailed specific theory about it. Any other questions? Okay, good. So yeah, I guess this is it. So now we can talk about the interesting part, that is why we want to beyond equilibrium. And we already know like a lot of the game theory classically are focusing on this is three type of equilibrium. And the first scenario we'll talk about is so-called rationalizability. This is a joint work with my student Yuanhao Wang at Princeton, and also two amazing collaborators, Ding Wen Kong, who was an undergrad student when we collaborated on this project, and he's currently a PhD student at MIT, and Yu Bai, who was at Salesforce when we were doing this project together, and he's now in OpenAI. So rationalizability. So first, this word sounds like not very familiar, but what does rationalizability mean? So rationalizability, by the words we say, we kind of we require the agent to be rational. So typically one criterion for the agent to be rational is we know like whatever the policy, whatever the equilibrium we converge to, we know the agent should never play like a dominated action. By dominated action means the action that is strictly worse than some other strategy can be either another single action or another mixed strategy, no matter what opponent is playing. So that is in all scenarios, this action is just strictly worse than some other stuff. So there's no reason we should play it. So this is just a very simple criterion. It's called like rational. Okay. For example, we can look at this very simple normal form game where every player have only two actions, and we can see in this scenario the second player. In this case, the action B when the action play B2, you get a reward 2 and 1. And if you play action B1, you get a reward 3 and 2. So no matter what opponent is playing B1 is always better than playing B2. So B2 is just dominated action. So a rational agent should never play this dominated action. So you can also make this slightly more complicated. It's called iterative dominance elimination. So you can basically do this eliminate dominated action multiple times. So we already say in the first time we realize this B2 is a dominated action, so we get rid of that. And now we now end up with a subgame because we know the second player will never play B2. And now in the second level, we notice because we already know second player will never play B2, so we only have the small games, and then we realize the A1 become a dominated action. So A1 is not a dominated action in the original game, but now becomes a dominant action in like first level or something like that. So you can iteratively doing this dominated action elimination, which ends up with some set that is we want to eventually convert to some set that is iteratively undominated action. Okay, that is after you do all the elimination, what is the action that is remaining? It can be one action, it can be multiple actions, and we're thinking those actions are reasonable. So this is also a reasonably classical concept, but in the game theory, but much less well studied. We define this rationalizability in terms of we just want to always play iteratively undominated actions. So in this case, it's like A2, B1 is in this game. But in other games, it can be like multiple actions instead of just having one actions. Okay, so this is a new criterion we're talking about. And we also can define the robust version that is not just strictly rationalizable, because in computer science, we can never do something like strictly. We always need to have some tolerance. So we say an action is delta rationalizable if it remains after iteratively eliminating delta dominated actions. So that is, we will only eliminate some action if it's a delta worse than some other actions. Okay, so this is a delta rationalizability condition. So after we have this definition or this new criterion of rationalizability, so first thing we want to consider is what is the relation between this rationalizability and the standard equilibrium, like a CE, CCE, or Nash equilibrium. Okay, those are like, so if the original concept is already rationalizable, then it's done and we don't need to do much. So it turns out we can first look at the exact Nash equilibrium and the correlated equilibrium. Both of them are already rationalizable, so they are very good. However, as we mentioned earlier, in computer science, we're never able to find exact Nash equilibrium or CE. We'll always find some approximate version of those equilibrium. And turns out approximate version of correlated equilibrium is already very problematic. So we can actually prove an epsilon correlated equilibrium. So I haven't defined what is the epsilon approximate version, but you can just think what is when you betray it, like your deviation, your gain will be smaller than epsilon. This is like what so-called like epsilon approximate correlated equilibrium. And such an approximate correlated equilibrium can actually be entirely supported on iteratively dominated action. Those are the bad actions. Those are actions we don't want. But those equilibrium can entirely supported on that. That is, I will just always play those dominant actions with a zero probability to play some other problem from some other good actions, unless I make this epsilon extremely small. That is 2 to the power of minus a. A is the number of actions for the game. That is, unless you are learning some equilibrium to some exponential accuracy, you won't be able to achieve this rationalizability by just finding standard correlated equilibrium. And to make things much worse, if you just want to find a coarse correlated equilibrium, they're not guaranteed to be rationalizable at all, even if you're exact coarse correlated equilibrium. Okay. We'll have some example here and reference. I think due to time limit, probably I won't run into this reference. But I think basically the intuition is for coarse correlated equilibrium, there are some cost when you betray the other player. You no longer see the shared random bits. So that's why a lot of equilibrium can even supported by in some dominant action that can still be equilibrium just because there are some cost of betraying others. Okay. So basically we know standard equilibrium concepts will not actually accommodate rationalizability, and also standard equilibrium learning algorithm will not be able to learn a rationalizable strategy. So the main question we're going to ask here is, can we efficiently learn equilibrium that are also rationalizable? Okay. So this talk will focus on the bandit feedback scenario. That is, we assume all the players don't know the game rule at all, and at each round we only learn the game from this bandit feedback. That is, every player will play some action, but we don't necessarily know what other player is playing. But I will just player I will just supplement one action at AI and see some random payoff UI, and that is A1 to AN. Sorry, I think in this talk we will assume in a setting you can observe what other players play. So essentially you're on some table, you can see what other players' actions, but you don't know the game rule in advance. So you will only learn the game by this random feedback, this UI A1 to AN, which you can think is like a stochastic version of the original payoff. Okay. So before we're talking about the interesting algorithm, you can think seems like there's a naive approach to learn the rationalizable equilibrium. That is, the equilibrium will fully supported on this iteratively undominated actions. Okay. Essentially we can do a two-stage approach. First stage is I will identify the set of delta rationalizable actions those are iteratively undominated actions. So we know those are good actions. Then in the second stage, I will just run some equilibrium finding algorithm on the subgame, which is only supported on this rationalizable actions. And this sounds like a very straightforward strategy to learn the rationalizable equilibrium. This is true, but not true in terms of some complexity issue. Okay. So you can actually prove if you are doing this two-stage approach, it inevitably will incur some exponential sample complexity, which is a to the power of n. where A is the number of action and N is the number of player. So you will suffer some like a curse of multi-agents or something, essentially that is exponential to a number of player. Yes.
You mentioned like satisfy a rational actions. Is because from your previous slides you mentioned to considering rational process. It seems like it can reduce your gain from a large scale to a small scale with the small actions. So through this type of rational process, it seems like your gain becomes smaller. And finally maybe it can left some state or maybe some points. And part of them, maybe one of them is equilibrium. Right? So that is like what you want to say is like
the rationalizable equilibrium. Yes. So essentially, you do this all the iteratively dominant elimination process, and you end up with the rationalizable actions, and then you learn the equilibrium. Those are the definition of a rationalizable equilibrium. Okay. So I will argue why this exponential sample complexity is required. Oh, by the way, I also want to say the intuition. When you do this iteratively dominated elimination, it's not necessarily will reduce to a much smaller game. It can be like reduce the size by a half or something like it. So it's not necessarily like going to significantly smaller games. Okay. So the reason we incur this exponential sample complexity is because the verifying the action dominance. Essentially, we can think if we say one action is dominated actions, we essentially need to say in all scenarios, no matter what other player is playing, this action is strictly worse than some other policy. That requires us to enumerate all the joint actions of the other players. So this enumeration is actually very costly. It scales exponentially with the number of players, which is why this is like exponentially large. So this sounds like some negative results, saying like rationalizable equilibrium are very difficult to find, just because even testing one single action is a dominated action or not is kind of quite difficult. But turns out we will have some algorithm which is able to find a rationalizable equilibrium in polynomial time. So I will just introduce the algorithm, and then we can talk about the reason behind it. So the algorithm is quite simple. If you still remember, the basic algorithm is the hash algorithm. That is this step we perform hash update, which is doing exponentially update, where we weight the probability according to the loss in terms of exponential way. So all we did is we just do some modification on the original hash algorithm. So the first modification is we no longer allow some arbitrary random initialization. We will first find a rationalizable action profile. That is a joint action, which is guaranteed to be rationalizable. And then we start our policy from there. This is our initialization. And then we also need to estimate the loss a bit careful. We cannot just use a fully stochastic loss. We need to do some mini batch. That is, we need to observe the loss for m times and do some average so that we are making sure the loss is under control. And eventually, when we output the policy, we just we have like full probability. We eliminate some small probability actions and renormalize the action. Okay, all those are small changes. Okay. So why this is a good algorithm? So I think the first thing I want to explain is in the previous slides we are saying identifying one rationalizable action or one dominant action seems like a very hard. But here in the initialization, we need to find one rationalizable action. So you might wonder, okay, this seems like this initialization is not doable. But turns out there's a very subtle difference which makes this possible. So in the previous slide, we were saying identify one specific action is rationalizable. Rationalizability is rationalizable is hard. That is, if you want me to tell you action A is rationalizable or not, this is very difficult. But on the other hand, if you just want to find one rationalizable action, it's not necessarily action B. It can be action B, it can be action C, it can be any action. I don't care, but as long as it's rationalizable, it's fine. Then finding one such action is not very hard. So this is why the reason we can actually do this initialization, because we don't actually know which action we're gonna find, but we're just gonna find one action. Okay. And then we're essentially doing this careful initialization and careful loss control so that we're making sure when we're doing this hash updates, because in the initialization, we're supported on this rationalizable actions. And then we're doing this mini batch thing so that we're guaranteed we can do the proof to guarantee that over the course of this hash updates, we will make sure this entire trajectory will remain to be quite rationalizable in some sense, and so that eventually we just do some truncation and we will get the good result. Okay, so this is like the intuition why this algorithm would work.
So you allow this thing to be played for m times. So this is not like a truly online betting.
Yes, I think this is assume like all the player are kind of like some sort of coordinate in some sense to figure out what is the equilibrium. So it's not like it's not the standard no regret setting where each player cannot talk and just play by themselves or something adversarially. Yeah, very good point. So this is the guarantee we can find. We can say. So we can essentially say the rationalizable hash algorithms is able to find delta rationalizable and epsilon approximate coarse correlated equilibrium in the following number of samples. That is lna over delta square, where n is the number of player, a is number of action, delta is this accuracy on the rationalizability. The only new parameter we introduced here is the L, that is the minimum elimination mass. That is originally, if you just do the iteratively dominant and how many times you need to do it before you reach to like final solution, like then you like no matter how many elimination you do, the game no longer change. This is like called the minimum elimination length. Okay, so it has both dependence on the rationalizability and epsilon CCE. And I think the most important thing about this theorem is this is the first polynomial sample efficient algorithm to learn the rationalizable equilibrium. And this talk seems most about the CCE, but we can also extend the same algorithm to finding a rationalizable CE by replace the no regret algorithm, which is hash here, to no swap regret algorithm. Then we're guaranteed to find a rationalizable coarse correlated equilibrium. So we can solve all the problem. We say the original equilibrium are no longer rationalizable, and by doing this modification, we're guaranteed the equilibrium we find is rationalizable. Okay. Any question about this part? Yes.
I guess that.
Go ahead.
No, go first. I think it's okay.
Why do you need the support of the policy in every round to be good if you just care about the final thing?
It's I think it's not necessary, but it's one way to prove our final thing is good. We tried a bunch of other techniques, but we kind of like realize in the middle, if it's already not unrationalizable, then it's very difficult to say what the end result is. So this is like one approach we achieved. Oh, another questions?
Yes, I guess my question here is your definition about rationalization, right? Is you need to somehow observe other people's action, right? To
you need to know the game rule.
Yeah, you know the game rule, which
Yeah.
means that you need to actually also look at, let's say, other players' actions to see, okay, whether your particular action is dominated by others, right? But then your hedging update, right? I guess you are doing this product policy, which means this A is like I only see my payoff. I don't necessarily use other people's action to update this information. So I'm just wondering how this can, this one is kind of like you're not using other information, but your definition of this rationalization needs.
Yeah, I think you actually implicitly has that information in it, because this algorithm is saying everyone is using hash. So this is different from the previous thing, like people can play different no-regret algorithm. This is like everyone playing hash.
Oh,
so you're essentially, because other players playing hash, so other players already like doing some elimination by themselves. So they're focusing on more like a good action. So that's why you can do this. Yeah, you're right. There's no free lunch, and you have to have some information like that, of course. Okay. So I guess if no questions, I will continue to talk about the second scenario, why I think beyond equilibrium learning is very important. I think I'm also very excited about this line. I think it's not super deep in terms of development, but I think when I started to work on this, it's like very surprised. This is a very important question, but seems like a very little understanding has been done. Little work has been done in this area. Okay. And this is by symmetry and equal share. And this is a joint work with my students at Princeton University, Jiawei Ge, Yuanhao Wang, and Wenzhe Li. So the setting is become very simple. So we just look at the symmetric games. There are tons of games in reality is symmetric because every player want to be fair. Like you don't want to just sit in some table where you're already on some like you're already on some disadvantage. So a lot of games are designed to be fair and symmetric to all the player. And for most of games, if you're like also including the random permutation on the seats, so that is you're like you for example you flip the coin in the very beginning and to decide where you sit, and then it's completely symmetric to all the players. And so this is the focus of this part that we want to talk about symmetric games. And for simplicity, we will also talk about constant sum games. For example, this either Mahjong or poker. So let's just say for simplicity, every game just have just have one winner, and the winner get reward 1, and other player get reward 0. So this is a constant sum. So no matter what happens, the summation of the reward is 1, or in this case C. And because in game theory, we know the constant sum, if you shift everyone's payoff by some constant, it doesn't change anything. So we can also make this as like a zero-sum game. So later we'll talk about zero-sum games. So constant sum, zero-sum is exactly the same. So the baseline we want to achieve in this game is we want to achieve at least equal share. That is, when we play Mahjong, this is like 4-player game. We want to win just 1/4 of the game. Or in this case, we want to achieve payoff that is C over N per game. This sounds like a very standard or very baseline thing. We hope like our super intelligence or like whatever superhuman AI is able to at least achieve this. Okay. So as we said, we will focus on symmetric zero-sum game. So the criterion is very simple. When we talk about the criterion, then we want to say whether standard equilibrium is able to achieve this criterion, that is equal share. So the answer, we can first look at the answer for 2-player zero-sum game, which is a very standard setting people looking at. In this subclass of games, the answer is actually very good. So first thing we know is Nash is unique. Nash equilibrium is unique. Unique in the sense that is, if you have some like action that are roughly equal, and of course you can like just change some probability among those 2 actions, those are the same. So other than this trivial like change, they are equal in the sense like the value are the same, and those Nash equilibrium are like connected to each other. And furthermore, the Nash equilibrium, Nash strategy is also known to be non-exploitable. This goes back to the very first question I think people ask in the Zoom, that is saying, is there some property that of Nash that can ignore what your opponent is playing? And this is basically that property. That is, if you're playing Nash equilibrium or Nash strategy in the 2-player zero-sum games, you can at least achieve 0 payoff. That is, you will at least draw with your opponent. You will never be losing, no matter what your opponent is playing. So you can easily understand in the rock paper scissors, if you are playing like the Nash equilibrium, that is a uniform strategy. In that case, that is 1/3 probability for all actions. Then no matter what your opponent is playing, you will never lose. Okay. But you may not win, but you will never lose. So this is a so-called non-exploitability. However, this 2-player zone is essentially the golden standard for so many years. But we can easily look at something beyond that, is a multiplayer zero-sum game. So this is what we're going to look at, multiplayer symmetric zero-sum game. By multiplayer, we strictly means the number of players need to be strictly greater than 2. And in the game theory, it's well known, Nash equilibrium or force equilibrium or all those different equilibrium are no longer unique. There can be multiple equilibrium, have different value. They are not connected to each other. They're just completely different. And furthermore, even in Nash equilibrium, the strongest like equilibrium concepts does not guarantee the equal share, even against the fixed opponent. That is, even opponent is not adapting to your strategy or to what you play, you no longer guarantee the equal share, or very basic baseline. So this is actually very simple to understand by looking at the very basic games, which is called like a 3-player majority vote. It's a very simple game. So just imagine we have 3 players. So ignore the picture, we have 3 players instead of 4 players. And it's doing majority vote in the sense every player only have 2 actions. That is, either you do action 0 or do action 1, or you can say action A or action B, whatever. So if everyone playing same action, everyone gets 0. Is it because it's a zero-sum game? But if a two player play one action and the other player play the other action, so the majority will get reward 1, while the minority get reward -2, so that the summation of the reward is 0. So this is my rule of a 3-player majority vote game. So we can see for this game, both 1, 1, 1, if every player play the action 1 or every player play action 0 are Nash equilibrium. Because if other two player play 1, then I have no incentive to change my action, because whenever I change my action, I'm going to lose. The same applies here. However, the exact problem is also because there are two unique Nash equilibrium. So you cannot just suggest, for example, if I have some AI agents who want to play this majority game, you cannot just suggest the AI agent to play Nash equilibrium. For example, if I suggest my AI agent to play action 1, what if the other player, 2 player, play 0, or have some probability which favor playing 0? Then I'm gonna lose. I'm gonna has a negative expected utility. So this is why neither action guarantees the equal share. So, and also I think a lot of previous paper kind of acknowledge that there's they don't really know what is a good solution concepts for this class of game. But nevertheless, this doesn't prevent a lot of prior papers or research groups. They develop practical algorithms for solving those games, because those games are actually important. A lot of people care about those games, like play poker, play Mahjong. So they designed this algorithm called cell play algorithm. Cell play algorithm is also very simple. Essentially, at every round T, you will maintain a policy that is theta T, which is a distribution over all actions. So all agents will play theta T. And then they just assign one agent to be the main agent. So they assign this agent to be a learner. So they make all agents to play the same policy theta T, but they will make the learner, the main agent, perform some updates, like can be gradient updates, can be hash algorithm, to update his policy to a new policy theta T plus 1. And you repeat this process. Then in the next round, all agents play theta T plus 1, and then you update your policy. So it turns out that this meta algorithm is the main ingredient for the SOTA systems, like when you want to play poker, like achieve the champion performance, or play Mahjong diplomacy. They all in some sense playing this cell play algorithm. However, we can easily see, first, cell play from scratch would not guarantee the equal share. Okay, this is like a restricted form that is saying if we start from nothing, cell play from scratch does not guarantee the equal share. And just because we can again consider a 3-player majority game. If we start scratch, then we don't really know what the other 2 humans are playing or what other players are playing. So in that case, I don't really know what action to suggest, whether play 1 or play 0. So no matter what algorithm I'm gonna doing, this is not gonna work. I see some questions online.
Well, I guess we can leave it to the end.
Leave it to the end?
Yeah.
Okay, that sounds good. So we'll actually talk later. Some other form of cell play also does not guarantee this kind of criteria in the experiment later. So hopefully I kind of convince you why the existing solutions are not really good in dealing with this equal share, very basic baseline for this symmetric games. So the question is, what is the right solution concepts to achieve this equal share? Okay. And when we have the right solution concepts, can we design some efficient algorithm for achieve this equal share? Standard questions, but for very interesting problems. So our observation first is, and in order to develop this solution concepts, we first have some observation is, this is like a symmetric multiplayer game. So opponents can play different strategy or can play same strategy. So the first observation is, whenever you admit your opponent to play different strategy, then there are games where your main agents can never achieve equal share no matter what she does. Okay. So there are also examples. Essentially, you can imagine there are 3-player minority game. So in this case, the reward is slightly different. Majority will get -2. Well, majority will get majority will get -2, while majority will get -1, and the minority get +2. So this is completely different. And in that case, you can see if two other players, one player plays 0, the other player is playing 1, no matter what you are playing, you will never be the minority and you will never be able to win the game. So this is essentially, this is a very simple, it already illustrates that if opponents are playing different strategy, then there's nothing you can do for some games. So takeaway here is we can essentially formalize this in terms of a minimax problem, a minimax like notation. And you will notice if you allow other player play different strategy, then this min-max is actually smaller than this min-max, where if you restrict other player to be the same policy, to be the same identical strategy. So we kind of like shows if we allow something like this, this will be sometimes will be strictly smaller than 0, so we'll never be able to achieve the equal share. So in order to consider the equal share problem, you somehow inevitably need to restrict your opponent to play the identical strategy. This sounds like a very strong like a restriction, because you never want to say, oh, my opponent has to be to play the same strategy. But it turns out, if you think about the prior system, the cell player, a lot of like online game, it actually makes sense. Because in the cell play algorithm, they already implicitly assume all the players are playing the same strategy. Okay, so this is how they design the poker system or Mahjong system. They kind of like already doing that. And also in the online game system, so imagine you are going to a casino where casino has like 100 people or 200 people in it. And imagine your opponents are just randomly sampled from this big pool. Then you can more or less like approximate your opponent's strategy to be identical for different players. Okay, so you can actually mathematically show this is approximately true. So the second observation is there are games where no non-exploitable strategy exists. I think where non-exploitable strategy does not exist. Sorry about this slides. So essentially, this is saying you cannot imagine something similar to zero-sum games where you have a non-exploitable, fixed non-exploitable strategy. In this case, that is, if your opponent is playing. If your opponent is playing, so this essentially says you need to choose an x1 that is a fixed strategy first. Then no matter what your opponent is playing, this is like non-exploitable fixed strategy. But we can say this is strictly than 0. So the only thing that is equal to 0 is your opponent first. If all your opponent first choose the policy, and then you choose some policy adapt to that. That is, you don't have any non-exploitable policy. Whatever that achieve equal share, you need to do some opponent modeling, and you need to be adaptive to the opponents. So the conclusion is, in order to achieve this equal share, most existing solutions would not guarantee equal share. However, if we do opponent modeling, and if we can like adapt to the opponent strategy, then we play best response to them. And this somehow is more or less the only standard thing that will guarantee the equal share. I guess due to time limits, I will just quickly say in the paper, we actually have efficient algorithm to find this solution concepts to guarantee the equal share. That is for both stationary opponents and for adaptive opponents. And eventually, we can also construct some experiments which shows that a lot of prior meta algorithms, if they don't stick with without study this solution concepts, directly design this meta algorithm. They are not general purpose algorithm in the sense they're not generic algorithm. You can easily construct some multiplayer zero-sum symmetric games where all algorithm will actually consistently lose to human player. That is, suppose some human player plays some fixed strategy that is not even adaptive. While our solution concepts will always guarantee you some equal share. Okay, I guess it's a bit fast because I'm running out of time. So the summary is very simple. We first talk about some standard game theory concepts where there are 3 different equilibrium, and we talk about algorithms to find it. And then later we'll talk about two concrete scenario where standard equilibrium theory is actually not enough to achieve some new criteria, very simple, important criteria we want to achieve, and how we're gonna design new solution concepts and a new algorithm to achieve that. Okay, I think this concludes my talk. Thank you.
Yeah. So coming and also explain to us about this very interesting concept and answer a lot of the that question. So maybe we can have time for, let's say 2 or 3 questions if you have.
Yes.
Yeah. Thank you very much for the topic. It's very So I have a very simple question about when you mention opponent model.
Opponent modeling.
Yeah. Yeah.
Yeah.
Yeah.
Model.
When we mention opponent models, it is for the just because you apparently you will play with other players. So that is just for the single player, just for yourself, or
for the main agents, yeah. For the main agents, in order to achieve the equal share, you have to somehow have the knowledge of the opponent. I think I think the counter example here, the 3-player majority votes, whereas in neither player will guarantee the equal share. The major problem is you don't really know what your opponent playing. If you don't know what opponent are playing, like playing, no matter what action you're playing, may not guarantee the equal share. Like,
yeah. So in that policy, is very benefit for the main player, main agent.
Right. It's like a yeah. I think this is also. I think you're right. Like a main agent has some advantage because they kind of like they model the opponents, and somehow opponents cannot change much or something. I think the reason we conclude this is because somehow this is a very hard game, and it turns out most other thing doesn't work. And this is there's all those strong concepts, but this is somehow unfortunately the only thing that is gonna work. Yeah, and but we also have some algorithm can dealing with to some extent dealing with some slowly changing opponents, but not like fully adaptive opponents. Yeah, very good question. Yes.
So these are for like competitive games, right? Zero sum. Is it also true that you need this kind of centralization in cooperative games as well?
Centralized.
Yeah. So like, well, this sort of opponent model, like you need to know what everyone else is doing roughly.
I would say.
Games, or?
I would say yes, because general sum game. So this is zero sum game because we want to, because I think a lot of the result is a little bit negative. So we're saying even restricted to zero sum games, you already like cannot achieve very good results. But I think for general sum games, zero sum game is one special case. So there are definitely some type of zero sum game will exhibit similar structure for it. I think a lot of them would apply there as well. I think there are also some online questions. So.
I guess the previous question is about the self-play thing, right? That the algorithm converge. The self-play one.
The self-play one.
Yeah, is there any theory to say these things converge?
Let me think. Okay, I suddenly forgot. I think we should have some answer. Probably. Okay. If you want me to guess, I think probably not. But I need to check it back. I think we should have some definite answer for it. I remember it's not necessarily converge to some policy, or it might be take a very long time to converge. But in all the simple examples we talk about it, so when you run it in practice, it will actually converge. Okay, I think the answer is also highly depends on what kind of updates you're doing. Like here, we can like leave out this updates is like a subroutine. So you can either do like gradient updates for when you do this new policy, or hedge updates. I think for hedge, probably you will have some guarantee. For some other updates, probably you don't.
Yeah, I mean, I think a very, very simple example where that would not work is like if you only have collections and each round you just say, in the first round you have A, and then the second round everybody picks B, then you just accelerate all the time between A. But if you don't have like diminishing but normally you would assume that you have these step rates to get converged.
Yeah, and also normally when you say the convergence, you actually say the average iterate convergence. Yes. So in that case, average is still convergent. Yes.
I have a question myself. Maybe I'm missing something, but can you maybe give some intuition why that self-play from scratch doesn't guarantee full share? Because everybody is doing like the same policy from the start. So for example, in the first round, let's say just
so the equilibrium will guarantee equal share. Yeah. That's true. But what I'm saying is I think all the motivation of this section is we want to essentially develop some like AI agents which play this game very well. So we're playing against a human player. So all we're saying like is like for example when you develop some system for poker mahjong, they're not assuming like you're playing some AI agents and you're play against 5 other AI agents. You want to test your ability of your AI agents against other human player. So I think the problem is, while you are playing this, where you are playing this end policy of the cell play, the other human may not play it. So yeah.
So, okay, so even in self-play, basically all the AI players, they play self-play, but like the human player might do something.
Might do something completely different. Yeah.
Okay, cool. Yeah, thanks for the question.
Thank
And also thanks to Shunyi again for talk.